Everybody. For today's morning session, we're going to have two talks again. The first talk will be by Daniel Agterberg, who will continue telling us about nodal excitations in superconductors. Just as a reminder, so the talk will be 45 minutes with 15 minutes for questions. Feel free to, well, as long as Daniel's okay with it, feel free to interrupt during the talk with questions. And at the end of the talk, you can raise your hand and we'll call on you then. So thanks very much and take it away.
Okay, thank you. And of course, you can ask questions throughout the talk. I'm perfectly fine with that. So let me just review what I did yesterday. So I'm talking about nodal excitations in superconductors, and I'm trying to argue that you get some new insight from topology and a much better understanding of typically occurring nodes. And so what I did yesterday is I went through a quick motivation, and then largely I went through a review of the classical single band case, where essentially we understand as nodes coming from group theory. And then I began, but only briefly touched on this nodal classification. And after that, I was going to give you three examples because there were three nodal classes that were relevant. But it turns out that I think that was far too ambitious for these lectures. And so I'm just going to give you two examples. One, which I think is the most amusing, is the existence of these Maglev Fermi surfaces in superconductors. And then the second one is to explain something I raised near the end of my lecture last time. I think it'll take me too much time to talk about the wild nodes in uranium tellurium 2. But let's just quickly review. Sorry, there we go. What I did last class, or last lecture, I guess. So I went through an argument to find the quasi-particle excitations in a superconductor, and I just show you the slide here. I'm not going to go over it again. For a single band superconductor, and in the normal state, we have both inversion and time reversal symmetries. Right? And so in that case there, you can find the excitation spectrum using a sort of unusual argument, but in the essence, you find the Pfaffian, and the zeros of the Pfaffian give you the quasi-particle zero excitations. Right? And so that was this result here. And so you find that the nodes, or the zero energy excitations, are given by points on the Fermi surface. And in addition, the zeros are given by the zeros of this gap function that we talked about a little bit today. And so typically we don't expect the zeros of this and the zeros, let me put my laser on actually, so you can see that better. We don't expect the zeros of this and the zeros of this to coincide. And so we typically expect to get points or line nodes in such superconductors, and we don't expect to get Fermi surfaces. And the second point I made was that the zeros of psi of k also gives us the zeros of the excitation spectrum. And so we can understand nodes by looking just at the structure of psi of k. Okay, the other thing I tried to emphasize was that we do need a better understanding of nodes. So I said nodes are given by character tables. In particular, if you look at the -1s in these character tables, they tell you that nodes can appear. And that's the symmetry argument. But in practice, many cases arise where we don't have any symmetry arguments for the existence of nodes, and we call these accidental. And here's one example from an iron-based superconductor. And then this is the interpretation of it, and belongs to an S-wave case. And another example I gave was that, again, in monolayer iron selenide, you find that an explanation for high TC in the monolayer could be that this is a D-wave state. But this D-wave state, I argued, is fully gapped. And so this is strange because the usual symmetry argument would suggest there must be nodes here, but they're not there. All right, and so I jumped into this homotopic classification of nodes. And then let me just briefly review the steps here. I'm going to go through this relatively quickly in the interest of time, but we started this. The first key step was to identify the relevant symmetries and symmetry classes. And then once we understand these symmetry classes, we find the dimensionality of nodes using codimension arguments. So we know what kind of nodes exist. And then once we know what kind of nodes exists, we can use homotopy groups to associate topological invariance with those nodes. And so I'm going to skip this last step in essence, and I briefly explained that yesterday. But let's just jump into then this process. Okay, so the key step I argued yesterday was that we should identify these, what symmetries we need to include in our theory. And I said the best symmetries for that are to include time reversal and inversion, because those are the two symmetries that allow superconductivity to actually be an instability. All right, so energetically, we know that we need to have time reversal or inversion or both to have a superconducting state. If we have neither of these symmetries, we generically can't expect to have a superconductor. And then I also pointed out that we generically have charge conjugation symmetries in all superconductors, and we did a little algebra to look at how that behaves on the Buggy-Baltishen Hamiltonian. And so to topologically classify the nodes, you want to look at symmetries that take K to K. And I should mention, there have been many topological nodal classifications, and the one I'm actually following very closely is this one by Thomas Bedusek and Manfred Siegrist. And the details are there, and the references here, and you can see it's a very long paper with a lot of, it's very well explained and has a lot of nice details to help you follow this more closely. But the key point is, these symmetries, time reversal, inversion, and charge conjugation, take momentum K to minus K. And so if we look at the products, time reversal times inversion, charge conjugation times inversion, and then what's called chiral symmetry, which is the product of these two, then we have symmetries that take momentum K to K. And then you can look at how these symmetries act on the Hamiltonian, and that's defined here. So time reversal times inversion takes H of K to H of K. Charge conjugation times inversion takes H of K to minus H of K. And these are both anti-unitary symmetries. So if those symmetries are present, then they square to plus or minus 1. And then finally, chiral symmetry, if it's present, takes H of K to minus H of K, right? These are the same symmetry conditions from the Altland-Zirnbauer classes that are known from topological insulators. And so the actual topological classification is already known for this symmetry classes. And so we can actually use their result directly, right? And so that's what's listed here. All right, and so what I want to do is just illustrate the second step of this process. So meaning we understand the symmetry classes, and we actually understand the topological invariants, but now we want to understand, just in a particular example, how do we get the possibility that there are, say, line nodes in one case. All right, and so what I want to specifically look at is this so-called class D3. And so here we see that time reversal times inversion squares to minus 1, charge conjugation times inversion squares to plus 1, and then chiral symmetry exists and is the product of these two. And so what we're going to do is construct a minimal model. And this minimal model will have pseudospin that I discussed in the last lecture, and also particle hole spaces and particle hole symmetry I also discussed last class. And these are going to be characterized by polymatrices sigma and tau. And what I want to do then is I want to impose these symmetries and ask, what is the kind of Hamiltonian that results from that, and what can we say about the energy excitation spectrum? And this will, if we can write down the general Hamiltonian for this, then we can figure out what kind of nodes are generally possible in this symmetry class. All right, and so here is the minimal Hamiltonian that will capture these three symmetries. It has 16 terms in it because there's 3 polymatrices plus the identity matrix. There's three spin matrices and 3 tau matrices plus the identity matrix. And then these coefficients must all be real because this Hamiltonian must be Hermitian. All right, so we have these 16 real variables, and now we're going to impose these 3 symmetries to find out that many of these 16 terms are actually 0. And the way we do that is we choose operators such that these conditions are satisfied. So let's start with charge conjugation times inversion. So here I already wrote this operator down before, and in particle hole space, it's tau x times the charge conjugation operator, because it's charge conjugation operator appears because it's anti-unitary, and it must satisfy the fact, it must satisfy this symmetry here. So let me make a brief comment as well. So when we look at the spin structure of this, we understand that to some degree. But the tau structure of the particle hole space, the matrices tau x and tau y, they correspond to superconducting pairing. And the matrices tau 0 and tau z correspond, excuse me, to the normal state, excuse me, normal state Hamiltonians. So the normal part, the particle hole, normal parts of the Hamiltonians, just so you get some bearing here. And that'll show up later. It's not too critical here. Okay, so let's impose this charge conjugation times inversion symmetry. That takes h of k to minus h of k. And so we just sandwich this Hamiltonian between this and its inverse, which is just the same thing. And when we do that, you find that because of the anti-commutation relationships of Pauli matrices, some of the terms vanish and some of the terms survive. And it's a good exercise to try to do this to see what happens. But you find that with this condition, only 6 of these terms survive, and then 10 of them vanish. And then you can impose time reversal times inversion. And here I took the usual time reversal symmetry. This is diagonal in the particle hole space, but it's I sigma y times kappa. So that's the usual case for spin 1/2. And then the chiral symmetry is the product of these two, and that's what you have here. And then you can impose those two symmetries as well. And of the 6 terms you have from charge conjugation times inversion, you find that only 2 terms survive, right? So there's only 2 terms that are non-zero, and that's the 0z term and the yy term. And the 0z term in the usual case is just the usual quasi-particle energy, epsilon of k. And the yy term is just the usual superconducting psi of k. You can see it's a pairing term because the second index is y. So only these 2 terms are 0. These must both be real because this was Hermitian. And so these are 2 anti-commuting Pauli matrices. And because they're anti-commuting, we can find the energy spectrum. And that's just plus or minus the square root of this squared plus this squared. And so we can now ask, do we have nodes in this energy spectrum? And to get nodes, we have to have this function is 0 and this function is 0. And when this function is 0 in 3-dimensional momentum space along a plane, this function is 0 in 3-dimensional momentum space along a plane. And so those 2 planes can only intersect along a line. And so we know in this class we're allowed to have line nodes. And so that's how we get that conclusion. And then formally we say this is codimension 2, which allows line nodes in 3 dimensions. Okay, so once we understand what kind of nodes we, sorry?
Can I ask a quick question about the previous slide?
Yes.
So you mentioned that the Hamiltonian is Hermitian. This might be a very silly question, but I don't see it immediately. This Hamiltonian is Hermitian. So you say that all the C's should be real? Shouldn't only the diagonal C's be real and the off diagonals can be?
That's a good question. The key point is that these matrices sigma and tau commute, and these are Hermitian matrices. And so then if I take the Hermitian conjugate of that, I'll take the complex conjugate of this, but because these are Hermitian matrices, that means these must be real. Does that make sense?
Okay, got it. Yeah.
Okay, so with those kinds of arguments, you can then construct what kind of nodes are possible. All right, I'm jumping ahead here. And so we can then look at all possible 10 of these AZ classes, but it turns out not all 10 can be achieved for these 3-dimensional superconductors. And in fact, only 4 of them can be achieved. And the simple reason for that is that in any of these cases, we must have charge conjugation times inversion symmetry. And I briefly touched on why that is the case, but charge conjugation times inversion squares to +1 for even parity superconductors and to -1 for odd parity superconductors. And those gives us then 4 classes, 4 different possible nodal classes with protected nodes. And then once we understand what kind of nodes we have, for example, if we have point nodes, then we can surround them by a sphere in momentum space, and we can see if that point node is topologically protected. And then in the 4 classes, we find that in 2 of them, we have point nodes that are topologically protected. And those 2 classes are this one and this one, but we can understand that as being an even parity or a spin singlet superconductor that breaks time reversal symmetry. Then we get doubly charged point nodes. And then in an odd parity superconductor that breaks time reversal symmetry, we get singly charged point nodes. And again, this 2 versus 1 just tells you the degeneracy of the nodes that we have in these 2 cases. So here we have 2 nodes, and here we have a single node in general. Conversely, if we have we can also look for line nodes, and that these are surrounded by a loop in momentum space, and we can ask if there's some topological invariant that protects those. And indeed, there is for this class here, which is a spin singlet superconductor that preserves time reversal. And we find that there is doubly degenerate line nodes, or sorry, the doubly degenerate line nodes characterized by integers. And then finally, there is a surprise in this classification. Oh yeah, so we're already able to answer one of the questions I raised before. I asked, how do we get accidental nodes? And it turns out this symmetry class tells us why we have accidental nodes. And that's because when we broke any spatial symmetries, but preserved time reversal symmetry in our spin singlet superconductors, we did not remove any of the symmetries that define this topological class. And so we know that generically we're allowed to have these line nodes, and that explains the appearance of these line nodes. These are line nodes because we have a c-axis coming out the third direction coming out of the page. And so we have line nodes that are still protected. And so that explains these accidental nodes. Now let me turn back to the point I was about to make. And that is that we find a surprise in this class where we have even parity superconductors that break time reversal symmetry. We find that these have topologically protected Fermi surfaces, something we did not see in the single band case. And so that's something I'm going to look into in a little bit more detail.
Can I ask a question?
Sure.
Regarding class C, so we have a chiral gap, but that wouldn't a point node correspond just to trivial solution when we have d equals 0?
Well, here these are the zero energy excitations of the spectrum. And so typically, so the answer to that question is actually no, and I don't have time to go into that. It's not as straightforward as that. If you have broken time reversal symmetry in an odd parity superconductor, you find out that the excitation spectrum is not simply given by the magnitude of d squared. And if that was the case, your answer would be right. But there's a correction term to the spectrum, which is proportional to d cross d star.
Oh,
and
the
so
anti-unitary. Gotcha.
Anti-unitary, exactly. And that anti-unitary term generically exists. And so what you're saying doesn't actually happen. So you do get them at finite d.
Thank you.
And unfortunately,
ask a question.
Sure.
Can you go to the previous slide?
Yes.
So you give an example of class D3. In this
Yes.
case, the surviving matrix is anti-commuting each other, so the energy dispersion is so simple. So
Yes.
but in general, the surviving matrix does not have to commute each other. So
Yes.
in that case, the number of constraint object nodes is not same with the number of surviving matrix. So in that case, how do I control these codimension analysis?
Sorry. Yeah. So I will actually briefly go over this for the class D as well, so we can understand the origin of the Bogdan-Lyubov Fermi surfaces using the same setup. And I will address this to some degree, and so you'll see that come up, but it won't be addressed as naturally. I mean, in the end, I think in each class you have to think about this carefully. So here, indeed, the remaining terms that existed had two anti-commuting matrices, and that made our life in finding the spectrum easy. So I did choose an easy case, you're right. But in each case, you have to look at it in a little bit of detail. But I will go over the class D in a few slides.
Yes, thanks.
Can I ask a question?
Sure.
So if we know the square of the Ti, Ci, and S operator, does that uniquely determine whether the gap function is even or odd parity?
Yes, in this case it does. And in particular, the Ci symmetry does tell you. So if Ci squares to 1, that's even parity. If Ci squares to -1, it's odd parity.
Okay, thank you.
Okay, so yeah, okay, so let me come back to this then. So what I want to do now is go through a couple examples of these symmetry classes. The first example I'm going to look at is the appearance of these Bogoliubov Fermi surfaces. So what this analysis tells us from topology is that they can exist, and they can be topologically protected. What it doesn't tell us is, do they exist in realistic models? And it doesn't tell us exactly what the topological invariant is for the cases it does exist and it is topologically protected. And so what I want to do now is turn to some more microscopic models and examine whether or not these Bogoliubov Fermi surfaces appear, under what conditions they appear, and then what is the topological protection in that case. Okay, so let me do that. And so let me just tell you what the key result is. So in even parity and clean even parity multi-band superconductors, in which the superconducting state spontaneously breaks time reversal symmetry, there's two types of excitation spectrums. Either the system is fully gapped, or it has topologically protected Fermi surfaces. So the line nodes or point nodes don't appear in these cases. We either have Fermi surfaces or it's fully gapped. And that's a surprise compared to the one band theory where we expected to see point nodes and line nodes. And the one example I will refer to a lot was an example I raised yesterday in the context of uranium, ruthenium-2, silicon-2, where we have 2 point nodes on the north and south pole and a line node in the middle in the usual one band theory. It turns out that when you go to multi-band theories, these nodes get what we call inflated, and they make this sort of, I guess, disk-like Fermi surface on the north and south poles, and this toroidal-like Fermi surface around this line node here. Okay, so let's see how this comes about. Okay, so here I'm arguing this applies to many materials, but I'm just going to jump ahead in the case to save a little bit of time. And so what I want to consider now is the simplest multi-band model I can come up with. And so the simplest multi-band model I'm going to consider has spin j equals 3½ fermions as opposed to j equals 1½ fermions. And this can occur in cubic systems, for example. And so we're going to also assume that the Fermi surface is spherical and the Hamiltonian has spherical symmetry, because that makes our lives easier and that gives us a simple problem to solve. And it turns out you can do many of the calculations here exactly. And so everything can be substantiated. So in this case here, we have 4 types of spin species, plus or minus 3½ and plus or minus 1². And we can describe these by spin 3½ matrices, which are just the generalization of the spin 1½ matrix. And then my Hamiltonian is a simplified form of this so-called Cohn-Luttinger Hamiltonian, which just has a diagonal term, which is just going to be a parabolic k² over 2m minus some chemical potential. And then it's going to have this spin orbit coupling-like term, which is just the inner product of momentum k and j all squared. And these j's, again, are these 4×4 spin 3½ matrices. So you can diagonalize this matrix, and you find that you get 2 bands, epsilon plus minus. The diagonal term from here survives, but this term just gives you a plus or minus beta k². And then depending on the relative size of this beta compared to, say, m, in this theory, you find that you get 2 bands that can cross the chemical potential. So if beta is small, you'll get 2 bands that cross chemical potential, or you get 1 band that crosses the chemical potential and 1 band that does not, and that's if beta is sufficiently large. And so the case for analytic purposes that I'm going to focus on is this case here, because we can do perturbation theory here, but this case here is actually in practice more interesting for finding these kinds of Bogoliubov Fermi surfaces. Okay, so that's our single band Hamiltonian. Now I want to make Cooper pairs in this Hamiltonian. And so I'm going to do the simplest thing. I'm going to consider on-site Cooper pairs made from these spin 3½ objects. All right, so usually we have 2 spin 1½ objects, and then if we make an on-site Cooper pair, there's only one possibility. We have to make an up-down minus down-up state to satisfy Pauli exclusion, right? Because we need to satisfy a local anti-commutation between these 2 fermions. But now we have 4 species of fermions, and so we can actually make 16 types of Cooper pairs in general. But we again have to satisfy the fact that we must have Pauli exclusion on site. And that means from these 16 types of Cooper pairs, we only have 6 left available. We have total spin 2 particles or total spin 0 particles. Just to give you a feeling of what these look like, here's a total spin j equals 0 Cooper pair wave function. And so it looks like a pairing between 3/2 minus 3/2, and its flipped partner, and then 1/2 minus 1/2, and its flipped partner. And you can see this state is anti-symmetric, so satisfies Pauli exclusion. And we can also express this as a 4x4 matrix, a gap matrix, as follows. And I won't really talk about this, but we can write this as some constant times the unitary part of the time reversal operator. And then this will give you your gap function that shows up in the MagLab Hamiltonian. And then you can treat the MagLab Hamiltonian as a 8x8 matrix as opposed to the usual 4x4 matrix and look at the ground states. Now I want to look at a broken time reversal superconducting state, so I can't look at this particular possibility. But in this channel here, the total momentum J equals 2 states, I can write down broken time reversal states. And here I choose a combination that's familiar. I write down something that's Jx, Jz plus Jz, Jx plus I, Jy, Jz plus Jz, Jy. And I say this is familiar because it's meant to remind you of the case where I had this Kz, Kx plus Iky like momentum dependent gap that I raised in uranium, ruthenium-2, silicon-2. And in that case there, we got these point nodes on the top and bottom and this line node in the middle. All right, and so now I have my gap function. I'm taking this local Cooper pair with total angular momentum J equals 2. And then I have the normal state that I described in the previous slide. And I can now go and look at the 0 energy excitations of the spectrum. I'm not going to go through the detail, but just tell you the results. What we find is, or what you can find, is we don't have the point nodes and line nodes as we had before, but rather we get the Fermi surfaces I've shown you before as well. And so in this simple 2-band model, the point nodes and line nodes we had no longer exist, but are replaced by these Fermi surfaces. Okay, so then we can look at more. So this model we can do analytically, and you can find these results fairly analytically. Most of it, I mean, it takes a little bit of numerics to find these Fermi surfaces, but it's not so difficult. We can look at more realistic models. And so here is this chiral D-wave state in strontium and ruthenium I briefly mentioned. This is now a 3-band system, but you can do exactly the same kind of process I just mentioned. And in this case here in this 3-band system, once again, you find for this kind of state, so here I write this down, but it's not exactly the state we consider. We consider some kind of local pairing state that has the right symmetry. And in this case here, again, we find MagLab Fermi surfaces as opposed to just the line nodes in the Kz equals 0 plane that we would have expected. All right, so in 2 examples then, we find that when we look at multi-band systems, you no longer have line nodes or point nodes, but rather you get MagLab Fermi surfaces. And so it seems like this is a generic feature of these theories. And so let's try to understand where it comes from. Okay, so the first place to do that is let's consider the symmetry class D and go through an analysis analogous to what we did for the class D3. And so here's the class D. So in the class D, we don't have time reversal times inversion symmetry. We do have charge conjugation times inversion. It squares to 1. But because we don't have time reversal times inversion, we don't have the product, so there's no chiral symmetry. And so there's only one constraint on this Hamiltonian when we write it out in pseudo-spin and particle hole basis, and that's this constraint here. And I already told you that this charge conjugation times inversion, which we choose in the normal way here, so this squares to 1, so satisfies this condition. We choose this, and then we implement this anti-symmetry condition coming from this. And we find now that the Hamiltonian allows 6 terms of these 16 in general from symmetry arguments. And again, this just follows from the commutation, anti-commutation of Pauli matrices. And so of these 6 terms, 2 are what we saw before. So this I called epsilon of k, and this I called psi of k. But now we find we get the cyx of k. It turns out here, this psi of k is just a real gap function. This is the imaginary part of the gap function. And so you can see it's in the x tau x channel. So it is some kind of pairing term. But these other three terms, cxz, czz, and cy0, they all sit in the normal part of the BDG Hamiltonian. And because they sit in the normal part, they have some sort of normal interpretation. And the interpretation of them is not so surprising. If we think about it and look at the form of the BDG Hamiltonian, we find that this corresponds to the existence of essentially a Zeeman field-like term, h dot sigma, in the normal part of the Hamiltonian. Right. And so, since these terms are not included in the single band case, the Bogomolov-de Gennes Hamiltonian Fermi surfaces must be a consequence of these terms here. And so they don't show up in the single band case. And so then we have to ask the question, how do they show up in the multi-band case? Because we know they must be the source of these Bogomolov-de Gennes, these Bogomolov Fermi surfaces. So where do they come from? All right, and so that's what this slide here is showing. Here I'm starting with this two-band system, and then of this spin j equals 3/2 case. I have a plus band and a minus band. I put the chemical potential here, and now I think, okay, well, this band is far away in energy. I should be able to just treat this band as a perturbation to this band here, and find an effective Bogomolov-de Gennes Hamiltonian for this upper band here. Right, and so if you do that, you get this form, which is like the form we wrote before. If you look at the normal, if you look at the pairing part, the pairing part looks very familiar. You get a usual spin singlet superconductor, and the form of the spin singlet superconductor is kz times kx plus iky. And just to be clear again, I'm using the same spin 3/2 local Cooper pair. That's this jx jz plus ijy jz form. And sure enough, when we go to the single band limit, it has the right properties. The interesting thing, of course, is when we look at the normal state part, so this part of the Hamiltonian, we get the usual single particle energy excitation spectrum. We get some shift in that spectrum, which is not too important for most of the physics we consider here. But we also get, indeed, this allowed h dot sigma, or this internal pseudospin magnetic field-like term. And when you examine its form, not surprisingly, this is perturbation theory. It comes as the order of the gap square divided by the energy difference between these two bands. All right, and so we can now ask, well, what does this existence of this magnetic field do to the spectrum? And so you can actually go ahead and calculate the Pfaffian like we did before. And remember, the zeros of the Pfaffian give you the zero energies of the excitation spectrum. And when we had zero magnetic field, I told you the Pfaffian was this term plus this term squared gives you 0, or that gives you the zero energy excitations. Now let's add this term here, and you can do that. You can add the Pfaffian, and what you find is you get the same thing as before minus the magnitude of h squared. All right, and so now when we want to find the zero energy excitation spectrum, that we have to set this equal to 0. But you can see I can move this h squared to the right-hand side. I no longer have the condition that this term plus this term equals 0, but rather I have this term plus this term equals something squared. And that's just a generic equation for a surface in three-dimensional space. And so we see that generically from this, we expect to see Bogomolov Fermi surfaces. So indeed, this h squared does give us the Bogomolov Fermi surfaces that we had before. And then we can look a little bit at the structure of this pseudospin magnetic field that's induced by the superconductor, and that I show here. And you can see it's relatively complicated. It points in different directions of momentum space, and it takes on all terms that are allowed by symmetry on the Fermi surface. And basically its role is then it takes the original nodes we had in psi of k, and then pushes them out so that we get these Fermi surfaces. So here's the actual excitation spectrum in the presence of H. And then we can actually calculate the determinant of the BDG Hamiltonian from this excitation spectrum. And you'll see that's the square of what I called the Pfaffian in the last slide. And so the physics then of this Bogomolov Fermi surface is indeed that once we have broken time reversal symmetry in the superconductor, the superconductor can generate a magnetic field, and that magnetic field then turns what were originally nodes into Bogusław Fermi surfaces. Okay, so we understand physically where this comes from.
Excuse me?
Sure, yeah.
I had a question about the Pfaffian argument, because the Pfaffian should only be defined for anti-symmetric matrices.
Yes.
But isn't the epsilon k minus mu on the diagonal? So shouldn't that be 0 by?
Yeah, this is a great question, and I've glossed over some details. But let me point out that so what you can show is the Bogusław Hamiltonian in the basis I've written here is not obviously anti-symmetric, as you just argued, but you can show there exists a unitary transformation that makes it anti-symmetric. And I haven't gone to the basis that makes it anti-symmetric. So you're right, but the point is we can apply a unitary transformation to H that makes it anti-symmetric. And so, yeah, that's done in a few places in the literature, but you show that there is such a unitary transformation because of the fact that Ci squares to +1. Does that answer your question?
Yes, thank you.
I have a question.
Yes.
Could you explain again why this gives, why the last equation in this slide tells us that there is a possibility for Fermi surface?
Yeah, okay, sure. Okay, so let's first look at this equation here, the one above it. So this tells us that we need two conditions to be satisfied to get a node, right? This must be 0 and this must be 0. And that's what gave us the line nodes in the class D3. But now we find that we no longer have the condition that this squared plus this squared must be 0. Once we have the magnetic field present, we find that this squared plus this squared must be H squared. And so the number of conditions we need to satisfy now is just 1, not 2. Does that make sense? This and this both had to be 0 in this case here. Now we only have one condition, and that means we generically satisfy a surface. So before, this gave us a surface and this gave us a surface. Those intersect in a line, that gave us line nodes. Now we only have this one condition, and we can satisfy that with a surface. Does that answer your question?
Okay, and what is the delta 0 in this?
Yeah, that's just some typical gap energy scale. In this problem, delta 0 is this the delta 0 in front of this jx jz plus I jy jz like term I wrote down a few slides ago.
Okay, so we are assuming delta 0 is non-zero.
Yes, delta 0 is non-zero. So this pseudospin magnetic field is generated by the superconductor through multiband effects.
Okay, actually, thank you.
Okay.
Daniel, can I also ask a quick question?
Sure.
If I go away from the special point, say kz equal to 0, then Hx has almost constant magnetic field. I mean, k dependence is there, but it's not crucial.
Yeah, you can look at it here if you want. Yeah.
We know what happens, well, you know more than well that what happens with superconductor in the presence of magnetic field. At some point it goes into FFLO state. Is FFLO a competitor to state with non-zero Fermi surface? I
mean, that's an excellent question. So the answer here is, again, it depends on the size of this magnetic field that's generated. But here the key difference is the magnetic field is of order delta squared in this problem. And in FFLO, the magnetic field is just a constant. So you have an energy scale you can vary independently. And so you can make it large enough to create it. So typically you don't find the FFLO state generated by this field. Yeah, so I won't go any further than that. I mean, you can, but there is more you could say about this question, and it's, yeah, but I won't go any further because just so we can move ahead a little bit.
Just one quick question. In the figure that you have in the middle of the point nodes, you argue that you would have Weyl nodes. What happens to the Weyl nodes when you go to the Fermi surface?
That's also an excellent question. The answer,
yeah, go ahead.
Yeah, so the answer to that is this Weyl charge that you had in this problem, which thanks to Andre's question yesterday, I said is plus or minus 2. You can now surround this Bogusław Fermi surface by another surface momentum space, and you can show on that surface momentum space we have no nodes again, And you can show that the Chern number associated with that surface is again the same as the Chern number here. So this still has, in that sense, this has a Weil charge as well as a second topological charge, which I'll mention in the next slide, that defines it. So the Weil nodes, in some sense, are still there in the sense that this topological Fermi surface also has a Weil charge. So it has a double topological charge.
Thank you.
So you still have a...
This has to do with some topological protection, I guess.
Yeah, I mean, the Weil nodes are very generic and, you know, they're hard to remove.
Right.
And so you would expect them to survive. So they do survive. And what was the other question I heard?
Yeah, my question is that, so you still have Fermi arcs then on the surface?
Yeah.
And how they look like?
I can show you later. I think I maybe re-ask this at the end or something, and I'll show you, because I have it buried in slides further on, not here, but I do have an answer to that question. It's interesting.
Okay, yeah, thank you.
Okay, all right. Okay, so here then I argue that this existence of these Bagouba Fermi surfaces because the superconductor generates this magnetic field. And so now we can come back to the topological protection, because we know that in principle there is a Z2 protection associated with these. And so it's been pointed out a few times in the literature that there is this Z2 invariant. And so the question is, what is the Z2 invariant? And so the answer turns out the Z2 invariant is defined through this Pfaffian. In particular, if you go from inside the Fermi surface to outside the Fermi surface, you find that the Pfaffian changed sign. And so you write this invariant as -1 to the power delta as the product of the Pfaffian for some momentum point inside the Fermi surface times the Pfaffian for some momentum point outside the Fermi surface. And if that is -1, then you find that you get a topologically non-trivial Fermi surface. If that is 1, then you get a topologically trivial Fermi surface. And you can show that, for example, the normal state Fermi surface is topologically trivial in this sense. What does this topological protection mean? It simply means in this case that the Fermi surface is stable to any perturbation that preserves this, well, I guess this should be C times I symmetry, not C times P symmetry. Okay, so meaning I can deform my Hamiltonian in many ways and I'll still have these Fermi surfaces. Also, because inversion symmetry is critical to the topological protection here, and that's what gave us the Pfaffian and allowed us to find the Pfaffian, it turns out that we don't expect to get any surface or edge states from this particular topological invariant itself, because the surfaces in these materials, physical surfaces, break inversion symmetry. And so we don't expect to have edge states associated with this. And numerically, we find this is the case. However, as I mentioned before, if there's an additional Weil charge, then you do find that you have edge states. And then, so this is work maybe, okay, that's been going on over the last 3 years. And there's been, I guess, one very interesting finding, I think, that's also happened very recently. This is by O and Moon, and I think O is here. And that is that these Bagouba Fermi surfaces, you can ask if they're unstable to interactions. And it turns out you can show that they are generically unstable to interactions. And in particular, they're unstable to a parity symmetry breaking interaction or inversion symmetry breaking interaction. And interestingly, that inversion symmetry breaking interaction is itself a BCS-like instability of the superconducting type that we saw before. And so I thought that's actually a nice, amusing result to understand these Bagouba Fermi surfaces. Okay, so that's what I wanted to say about the Bagouba Fermi surfaces. And now I want to go to the other story I wanted to tell, which were nodes in class D3. And this is, again, this time reversal invariant spin singlet superconductor. And I wanted to address this question I raised in the context of the monolayer iron selenide. So in the monolayer iron selenide, I told you yesterday that these have, when you grow them on, say, strontium titanate, these have the highest TC in the iron-based superconductor family, depending on who you ask, somewhere between, say, 40 and maybe even 100 Kelvin. And people have done careful ARPES studies on that and have found that you have two electron-like Fermi surfaces that surround what is known as the M point. Sorry, the M point is in here. And then again, these ARPES measurements have, so we've these two ellipses approximately that cross each other. And then you can measure the gap on these ellipses, and you can find that the gap is everywhere constant. And so there's no nodes from ARPES. And so in some sense, it looks S-wave-like, but then I argued if you really believe you have electron-electron interactions, then you'd expect to have some nodes or some zeros in the gap. And there's a natural explanation for these two bands then is to have a sign change between this band and between the two ellipses. And then I argued that if you look at the symmetry classification of that, that must be a D-wave superconductor, not an S-wave superconductor. And so we would expect to have nodes where these two bands cross each other. And so the question is, where have the nodes gone because they're not seen experimentally? All right, so let's look at that a little bit more closely from this topological perspective. All right, and to do that, I need to make a minimal theory to understand this. And I'm not going to go into the details of that, but just write down the form of that theory here. The key point is because we have two bands, it's not sufficient to have just two spin degrees of freedom. We need to have two additional orbital degrees of freedom. And there's a very nice paper by Cechevich and Vafik that talks about the origin of these 2 degrees of freedom at the M point of this monolayer iron selenide. But you can then define orbital polymatrices and spin polymatrices. And then you can write down a 2-band Hamiltonian, which has a usual kinetic term. And then it has this orbital part, that's kx times ky times tau z, so it's plus and minus. And these two terms then gives us, if we ignore this last term here, this gives us 2 ellipses that cross, much like the band structure that's seen. But in principle, there's also this spin orbit coupling-like term, which mixes orbital channels and spin channels with momentum. And that's characterized by some parameter v as 0. And in ARPES measurements, it looks like this energy scale associated with this is very 0 and is very small, nearly 0. So we get something that looks like 2 ellipses crossing. And so loosely speaking, 1 ellipse here and 1 ellipse here. Okay, so here for this 2-band model, I've written down some parameters and looked at the structure of the Fermi surface here. And I point out that at 0 temperature, the typical energy scale, the gap is about 11 milli-electron volts. And these are all in milli-electron volt energy scales as well. Okay. All right, so this gives you something that looks like the band structure. And so we have a normal state Hamiltonian. And so let's first solve the problem without the spin orbit coupling so that the normal state is these 2 ellipses that cross each other. And let's just, I'm not going to go through the details of how this originates. Let's just assume that we have D-wave pairing. All right, so D-wave pairing then means that the gap on one is opposite sign of the other. But of course, we can write down so I can write down a gap on one ellipse like this and a gap on another ellipse like this. And it can have some dependence on phi as we rotate around this ellipse. And we can write down 2 types of D-wave terms, a usual D-wave term where the rotation dependence is the same. I should mention these phi's differ by pi by 2. So it's a little bit, it takes a little thought to understand this, but nevertheless, I can write down a D-wave form factor times something that's the same sign on both these bands. Or I can write down a constant term that's of opposite sign on these 2 bands. So this I'll call the usual orbitally trivial D-wave superconductor, and this I'll call the orbitally non-trivial D-wave superconductor characterized by constant. And so it's this orbitally non-trivial that doesn't have nodes, but this orbitally trivial case will have nodes here. So that's the usual case that we understand and the nodes show up. Okay, so the orbitally non-trivial solution is the strange one, and it should have nodes. And so how do we understand that? Well, the first thing we can do is we realize that we set a term allowed by symmetry to 0. So let's put that term non-zero and make it relatively large. And so here I've made it large enough to actually show you that what happens with the orbitally non-trivial solution is, in fact, we do get the nodes reappearing. So the spin orbit coupling will induce those nodes. And there's 2 nodes, one on each band. The bands now don't look like 2 ellipses crossing, because where the ellipse crosses, you now have an avoided crossing from this coupling term. And so we see the nodes. Okay, so the reason the nodes didn't appear was because the spin orbit coupling was small. But then we can ask what happens as we reduce the spin orbit coupling? Why do nodes disappear in one case and not the other? And so here is where the topological properties come into play. It turns out that these nodes are protected by a time reversal times inversion symmetry. And sorry, I have P here for parity. So it's protected by chiral symmetry, and those gave these plus or minus 2 charges I mentioned before. And you can compute these charges for all these nodes, and you can compare the orbitally trivial case to the orbitally non-trivial case. And what you find is that in the orbitally trivial case, if we have the 2 nodes here, then we find that the charges for the 2 nodes on the 2 bands that sit close to each other are the same. All right, so these are both +2, these are both -2. However, if we look at the orbitally non-trivial solution, you find that the charges associated with these nodes are opposite. And so the nodes sitting close to each other are opposite. One has +2, one has -2. And now you can begin to understand what happens as we reduce the spin orbit coupling. These nodes begin to approach each other because we're removing this avoided crossing. And in fact, they annihilate. And when they annihilate, the nodes get removed. And so we can understand the removal of the nodes as a consequence of the fact that we have 2 charges that are opposite for these nodes that sit close in momentum space. And so we can push this picture, we can choose some intermediate spin orbit coupling value, and we can see, do we indeed reproduce the experimental picture once we have some intermediate spin orbit coupling? And indeed, we do reproduce the experimental picture. I've shown that here. Here's a picture of the gap structure for some smaller spin orbit coupling. And sure enough, you find that now these gaps no longer have nodes. And the understanding is because the 2 opposite charge nodes have actually met and annihilated with each other. And so this provides a nice way of understanding this experiment, which is a topological understanding that goes beyond the usual symmetry understanding in the context of these more general type of superconductors. Okay, so that's what I wanted to say about class D3. And as I mentioned, I think I really don't have time to go over the nodes, while nodes in the context of uranium tellurium-2, because I think I'm very close to the end of my time. And so let me just come to my conclusions. I hope I've convinced you that topology and symmetry arguments combined together give you a more complete understanding of nodes than just the usual symmetry arguments we've had before. Than we've had before. In particular, using the 2 symmetries that stabilize superconductivity, you get a nodal classification that allows surprisingly new states like topologically Fermi surfaces, topologically protected Fermi surfaces, in addition to the usual points and line nodes. I told you why these Bogdanov Fermi surfaces appear. They're a multi-band effect, and the multi-bands give rise to a pseudo-spin magnetic field in the superconductor. And I showed you that sometimes annihilating nodes can also cause surprises, meaning that the usual symmetry required nodes can disappear, and we can understand that from having topological nodes of opposite sign. And then what I didn't discuss is that you can have while nodes at non-symmetry locations in class C superconductors, but I won't go into that in any detail. All right, thank you.
Okay, so we have about 10 minutes or so for questions. So we'll start with Andre.
Oh, put me last.
Okay, I'll put you last. Then Dimitri.
Thanks. Thank you for the talk. Could you just say a few words about the uranium telluride case?
Okay. Yeah. The reason I can. So let me. Okay. So maybe I'll talk about the nodal structure there, because I guess this is what you're asking about, right? In the end. Okay, so let me skip the part where I say this is a spin triplet superconductor and why we believe it's a spin triplet superconductor. Let me also skip the part of why we believe it breaks time reversal symmetry. Let's assume it breaks time reversal symmetry and assume it is spin triplet, okay? And so then let's jump then to the nodal excitations. And let's assume now that we have a broken time reversal odd parity superconductor. And so then in the gap structure, we can have 2 D vectors, D1 plus ID2. D1 is a vector and D2 is a vector. And in principle, by symmetry, we're allowed to have this I between the two components. And so for this gap structure, which is relatively complicated, as you say, it's non-unitary, we can calculate the quasi-particle excitation spectrum. And this was done years ago by actually Manfred Siegrist in the early 1990s. And so in the single band case, you get the usual term that gives you the Fermi surface. You get the magnitude of the gap squared that's very similar to the singlet case, but then you get this plus or minus the magnitude of this Q term. And here Q is this I D cross D star. What's important to note here is you can show that D squared minus the magnitude of Q is a number that must be greater than or equal to 0. And so you can treat these two as two separate gaps. And loosely speaking, you can say that your normal state has split into two spin polarized surfaces, and each of these spin polarized surfaces have a different gap, delta plus or delta minus. The one that's interesting for nodes, of course, is the case where D squared minus Q equals 0. And so you can examine how that can occur. And so this is like the codimension arguments I was talking about before. You can examine the possibility that the D squared minus the magnitude of Q is 0. And you can show that that happens if you satisfy two conditions. One is the magnitude of D1 and D2 are equal somewhere in momentum space. And the second one is the inner product of D1 and D2 must be 0. And so you can then argue, you can think about what this means. This tells us to get a node, we must sit on the Fermi surface again. This tells us we have a second condition that D1 equals D2. So that defines a surface in momentum space. Then the inner product of D1 and D2 also defines a surface in momentum space. And so generically we have three surfaces and those can intersect at a point. And so we find that while nodes can generically exist. All right, so I think that partially answers your question there. And then, so for uranium tellurium 2, we argue later that not do they only generically exist, we actually have good arguments to say they do exist in this material. And that's what this slide talks about here, but I won't go into that.
Thank you.
Okay, so we have a question from Kwansen.
Oh, hi, thanks for the lecture. So my question is about the Bogoliubov Fermi surface. So in the example you have shown here, that Fermi surface comes from that only one constraint equation. I'm just wondering, it is necessary that the Fermi surface here is closed? It seems like the example you've shown here, the Fermi surface is closed.
Yeah, the Fermi surfaces are closed, absolutely. Yeah, so these are not, I mean, yeah, so these are not going to give you arcs.
Okay, thank you. But why is that?
I mean, so that's the usual case, right? Fermi surfaces that are not closed are Fermi arcs, for example, and there's some additional topological reason for them to exist. We don't have such a topological reason for them to exist here. So I think that's the simple explanation.
Okay, thank you.
Next, we have a question from Tianlei.
Hi, thanks for the great talk. I have a question about like the slide of the do you write the superconductor classes? So write down like things like charge on S0, S1, and S2 spaces. So what does that like physically means here?
Yeah, so what is, okay, so yeah, so here I talked about what is the surface S squared, what is the surface S1. I never specified the surface S0, right? I think that's what you're asking, is that right?
Actually, I'm not sure like what's S2 and S1.
Yeah, okay, so S squared just simply means a sphere in momentum space, and that sphere surrounds a point node. And so on that sphere, because it surrounds the point node, the spectrum is fully gapped. And because the spectrum is fully gapped, you can use the kind of topological arguments you have in fully gapped materials. So follow the arguments that lead to the tenfold wave, for example, in the context of topological topological insulators. And then you can show that associated with this surface and momentum space, you can have a topological charge. And so on the surface momentum space, we can define a Chern number, and that Chern number is the topological protection for the point nodes. Conversely, if we have a line node, then we can draw a little loop in momentum space, and I have a picture of that loop back here. So here's a loop, and then we can calculate a winding number charge on this loop, and we can show that that's a topological invariant in this particular symmetry class. And then finally, if we have a Fermi surface, then the only surface or momentum space surface that we can create that surrounds it in some sense is if we take a point inside that surface and another point outside that surface. And then we can compare things inside the surface to outside the surface. So that's the surface S0. It's 2 points, one inside the Fermi surface and one outside the Fermi surface. And that's where I discussed this Pfaffian invariant in that context there. Does that explain?
Yeah. So they all means like topological charges. What do you mean by charge here?
Exactly. So on those surfaces, the momentum space, we can define topological charges. And those are those charges that we give here. And those topological charges are defined by these homotopy groups listed up here. And I just haven't, I've really glossed over those details because it takes quite a while to explain.
Thank you.
Okay, so we have 4 more hands raised. In the interest of time, let's have those be our last 4 questions. So first from Luis.
Oh, thank you. So Daniel, I mean, how generic is this argument for Bogoliubov Fermi surfaces in generic multiband superconductors? Because we gave examples, transrutinate, something that looks like Renyi-Ruthenium 2 silicon 2, but it would seem that it could be a quite generic. And would we have Fermi surface in superconducting state, let's say the iron-based superconductors, the symmetries do not allow them. And the other question is, can we detect those, let's say, with quantum oscillations? You know, these are not, in these materials, I know Renyi-Ruthenium 2 silicon 2, they have seen nice oscillations in the superconducting state, right? Mm-hmm. But in general, it's not easy to see quantum oscillations in the superconducting state because of this. There's a damping factor associated with the superconducting gap.
So first, they're very generic whenever you have an even parity superconductor that breaks time reversal. And that's what this perturbation argument shows you. You can show quite generally, you always get this pseudospin magnetic field. And so it's easy to generate it. The only question is, how big is this pseudospin magnetic field? What energy scale? And in cases like strontium ruthenate, it's not such a big energy scale. And so you actually have relatively small Fermi surfaces. But in heavy fermion materials, you can expect this energy scale to be much larger. And then you can, I think, get observable Fermi surfaces. And let me also, so I think it's generic. And then your other question was quantum oscillations. These are Bogoliubov Fermi surfaces. And so if you integrate the charge associated with all the excitations on a Fermi surface, that integrated charge must be 0. And so they're different than the normal state Fermi surfaces where we have nice quantum oscillations coming from the fact that normal electrons have charge. And so the question of actually seeing Bogoliubov Fermi surfaces in quantum oscillations is somewhat subtle. It is possible that your Bogoliubov Fermi surface breaks up in regions that have positive charge and regions that have negative charge. And then you can see oscillations from the different regions or something like this. But that is not going to be very generic, and that's going to have to involve, I think, some sort of special type of Bogoliubov Fermi surfaces, something which we haven't really addressed yet. So I think quantum oscillations may see something, but it's not a generic feature that you expect to see in all these cases here.
Okay, we can discuss that later.
Yeah, okay.
Okay, another question from Hanbit.
Thanks for a nice talk. And I have 2 quick questions. First one is about the disorder effect. So I knew that even in the case of line node superconductor in 3D system, if there is an infinitesimal disorder, then the disorder can induce the residual density of states. So it seems like a Fermi surface. So do you know? Can you identify the Bogoliubov Fermi surface and line node superconductor with disorder?
Yeah, so that's a great question. So it's not obvious. For example, specific heat might be one way to look for a Bogoliubov Fermi surface because there'd be a residual density of states. But that residual density of states, as you point out, also appears if you add disorder to a class D3 superconductor. And so it is not obvious that you can differentiate. And so you'd have to do some careful disorder studies to understand if there's an intrinsic contribution there or not. Transport studies might be a bit better, though there you need to, so for example, I did mention briefly in the last lecture, the possibility of this so-called universal thermal conductivity. that happens for line nodes in D3 superconductors, where you get a constant term in kappa over T, and that constant term is independent of impurity scattering. Now, because of the existence of these Bogdanov Fermi surfaces, you do expect to see some impurity scattering dependence to that, because there's an intrinsic contribution as well. And so there may be a promising way to look for this. But again, so you raise a good point, and I think there may be ways around this.
Yes, thanks. And the second question is about the sponge oscillate. And
yes.
I saw some paper with that paper some group argue that the system is D plus IG, which is the multi-component pairing symmetry. And my question is that, can your D plus ID scenario be compatible with that theory? I mean,
no. So, okay, in some sense, yes. Yeah, so this is a proposal from Steve Kivelson's group, right?
Yeah.
That, so it turns out right now, I think there are two explanations that are compatible with all the experiments for strontium-ruthenate. That is this chiral D-wave state, which I prefer because these two channels, KZ, KX, and KZ, KY, are degenerate by symmetry, right? So they have the same TC. Once we have any tetragonal symmetry. In the case of this D plus IG case, formally that is something like B1G plus IA2G pairing symmetry. And so those belong to two different symmetry channels. And so it has to be argued that there's some reason for those two different representations to have similar TCs. However, there are certain aspects of that state that also explain aspects that are not explained in this case, and that has to do with this jump this has to do with ultrasound measurements, where they see this transverse ultrasound jump at TC, and both the states, this state and the D plus IG state, are compatible with this jump, but the D plus IG state also predicts zero jump in other transverse states. And as far as the experiments so far see, they don't see a jump in those other transverse states. However, they also argue they don't have the resolution to see it. So these are two, I say, competing scenarios for the order parameter in strontium-ruthenate. Both are consistent with experiments, and I think it's going to take time to settle which actually is right and which is not. But by the way, both should have Bogdanov Fermi surfaces.
Yes, it makes sense. Thanks.
Okay, question from Jeremiah.
Hi, I have two questions. First of all, is it correct to say that this analysis applies to generic K points and that at high symmetry points, other symmetries can make the picture more complicated?
Yes. In fact, I was going to make that point in the case of uranium tellurium 2, if I had the time to go over it. So let me just show you what the point I was going to make was. So here, the picture is you get Weil nodes, and these Weil nodes sit at generic symmetry points momentum space. But you can ask, what happens if you restore time reversal symmetry in this odd parity superconductor? We expect to get no nodes, but what happens is these oppositely charged Weil nodes, they approach each other, and they'll join at this point here. And the remarkable thing is that in this case, you find that actually a node still survives, even though you have two oppositely charged Weil nodes. So plus and minus, you'd expect to annihilate to give you a gap, but you get something that survives. And that something survives because we have additional symmetries in the problem. So symmetry imposed nodes still exist, and but they're not in the topological classification I included, because I considered those symmetries to be less important than time reversal and inversion. So I think because those are the symmetries needed to stabilize the state, and the other symmetries can be controlled other ways.
Sorry.
Yeah.
My second question is, does this analysis exist for bosonic BDG Hamiltonians?
Sure. There's no reason why not. Yeah, so that just depends again on the behavior of these symmetry operations, right? C and T, etc. I mean, I haven't thought about that carefully, but I see no reason why it shouldn't apply in those cases. So The classification I gave you is specifically for superconductors, but there is, of course, a broader nodal classification, and that broader nodal classification should in principle apply.
One last question from Andre.
Let me be quick. Daniel, specific question about strontium ruthenate.
Yes.
As you know, I think you're talking about two orbitals, XZ and YZ there.
Three, actually, but
so XY
yeah.
is also needed. Okay.
Yes.
Question. What is known about orbital structure of this Bogoliubov Fermi surfaces? Does it have any interesting orbital composition?
Yeah, okay, so actually you can answer that question. I mean, we do understand this is really for people who are familiar with the Fermi surface of strontium ruthenate, but you can clearly in this picture see the usual normal state Fermi surface of strontium ruthenate. And if you remember that this band here is meant to be largely XY orbitals.
Exactly, yeah.
And this band are XZ-YZ orbitals. And so now you can see that it really looks like on these XZ-YZ orbitals, the Bogoliubov Fermi surfaces appear to be the largest. I understand, okay, I should say there is more to this. I can discuss this more with you, but how we understand this picture. But that would be the answer to your question.
Yeah, and you assume that the gap is the same in all Fermi surfaces.
Well, okay, we assume that the local gap is the same, but then when we project that out onto the Fermi surfaces, you do get some anisotropy. So it's not necessarily the same on all Fermi surfaces. But I can show you other figures of that. They are comparable. So there's so I think that answers your question.
Okay, I might contact you later about this. Yeah, I'm just curious.
Okay.
Yeah, thanks.
Okay, so we went a little bit over time. Why don't we take a 5-minute break or so and meet back here close to 10:15 for the next talk. Well, close to 10:20 for the next talk by Andre Bernovig.
Dan, I have a question for you. If
Sure.
you still have a second.
Sure.
Would these Bogoliubov Fermi surfaces show cone anomalies? And
in principle, they should.
So then there would be a nice way to distinguish from the disorder, right?
Yeah, that's a good point. That would be, yeah, I mean, that's a good idea. Yeah.
All right.
Then let me also ask a trivial question. This is about stability of Bogoliubov Fermi surfaces.
Yeah, that's a good question, actually. Not really
no, I didn't ask it. It's like this. It's just the more I hear about this, the more I'm amused about this. But suppose you have some, say, arthrombicity in the system, and you add, by whatever reason, you add a constant gap to your KX, KZ gap, plus IKY. Then is it true that you have to compare magnitude of the gap of S-wave gap delta with square of the other gap? Because your H is delta square.
Yeah, that is, right? Yeah.
So in this respect, yes, everything is stable, but there is another parameter which you can measure, mainly magnitude of the gap. And then you may destroy this instantly because you compare linear and quadratic terms in the gap.
So, I mean, so we've actually looked at adding a constant gap like the one you mentioned, and it doesn't remove the Bogoliubov Fermi surfaces at all. And you can make the two types of gaps comparable. So what it does do is changes the size of the Bogoliubov Fermi surfaces. And
but don't we have to compare delta, constant delta and delta squares that coming from H? What do you call delta naught square? Let's call it delta naught square and delta 1, which is constant.
Well, it's not so simple because the point is that it's where H is important, where delta goes to 0, and delta goes to 0 by symmetry. So maybe in the example you say, you add a constant gap with orthorhombic symmetry then you do add a, then I can see indeed you're making delta too big to make the Boglu-Bott Fermi surface, and you'll come to a fully gapped system. I think that's what you're asking, right? Yeah, so I think that's
and
right.
The argument is that you compare linear term in one gap and quadratic term in the other gap.
Yeah, that's right. So now if we break the symmetry, it is possible to remove the Boglu-Bott Fermi surfaces this way by adding gaps that don't vanish near the Boglu-Bott Fermi surface.
Exactly.
I agree.
Yeah. Exactly.
So Andre, do you want to just make sure that your slides are working and share your screen and just check all of that?
Yes, thanks.
Yeah.
Also, hey.
I'll just
Hi,
do hey, I'll just do whiteboard if that's okay.
Okay, sure.
Let's see. Ready. Okay, very good. It's working.
Great. Perfect.
Thanks.
I like the beard.
Huh?
I like the beard.
Yeah. Yeah, tough times all over.
Is it COVID production?
It's yes, it's COVID studios. Yeah, what can you do? It's really a tough life. How's your hair, Andre?
Well,
I may ask so. Weird question. Yeah, I said if I may ask so. How's your hair? Weird question.
Well, it still exists.
Yeah, sure, but getting longer, shorter.
Well, actually, we try to be reasonable, I would put in quotes. So we have a guy who is working as a hairdresser, and he helps us. So we're okay with this. Yeah.
I see. Okay.
Yeah.
Barry stayed constant.
Yeah, pretty much.
Yeah, when we'll be able to travel again, we're not going to recognize each other.
Yeah, that's a potential problem. Yeah.
Okay, we can wait 2 more minutes just so well, 1 more minute so we start at an even time. So.
Andre, what do we do if we cannot understand your writing?
That's a that's a very good question.
Yeah.
Well, I guess I will apologize.
Okay, welcome back, everyone. Let's get started with our second talk of the day. It's a pleasure to have Andre Brnovig here to tell us more about twisted bilayer graphene. So thanks, Andre.
Thank you, and thanks everyone for powering through this week. A set of very interesting talks. So what I wanted to talk today about a little bit is the physics of twisted bilayer graphene and twisted trilayer graphene, or at least, well, part of the physics of these systems. And you know, this is obviously work done with several people. Most of them are cited here, but of course there's many other people that I have to thank, which are not in this list. So if you're in the audience, I apologize. So most of the things that I'll be talking about in twisted bilayer were done with these people, and then twisted trilayer will be work done with Dimitro that I'll be talking about. But basically, I kind of want to give a very basic introduction to the physics of these two systems in the way that we sort of understand it. So I wanted to point out that there's two approaches to the problem, and I'll be talking about one of them. But the two approaches kind of, they're all based at the very basic scale on this kind of remarkable Hamiltonian, which is called the Bicester-McDonald Hamiltonian, which we call the BM Hamiltonian. And this is really a series of Hamiltonians, not only one Hamiltonian, but it's a series of Hamiltonians that can be applied to twisted bilayer, twisted trilayer, many other twisted problems. It pays off to kind of delve a little bit into the physics of this Hamiltonian. So the two approaches actually are complementary, and one of them is the real space approach to this Hamiltonian, which was really pioneered by Oscar and Jan, so Buffett and Kang. And then there's the momentum space approach, and there's kind of complementarity between them that I'll mention when without going into many details. I'll focus today on the momentum space approach because that one I personally worked on and we worked on, but I wanted to point out that there's these two really kind of complementary approaches to the problem. Now, I want to delve a little bit deeper into the physics of this Bicester-McDonald type Hamiltonians and show you two things. Thing number one, that it's not only that these Hamiltonians are not only numerically tractable, but also sort of analytically tractable in some certain ways. And they allow a series of approximations, most of which I'll go through, which basically give you a sense of you know, the order of energy scales in the problem and what should be neglected and what should not be neglected in the problem, and then that they have a series of symmetries, and this is true for both the bilayer graphene and for the trilayer graphene. And they have a series of symmetries that basically almost kind of generically renders them topological, whether they are topological anomalous with gaps between the flat bands and other bands, or without gaps. There's a sense in which you know, a lot of these Hamiltonians are topological. So and then, you know, this has a lot of influences also on the interacting problem, non-interacting problem, superconductivity, that I'll try to go through. Okay, so these Bicester-McDonald Hamiltonians basically are a plane wave sort of continuum momentum approach, where if we take a single layer of graphene and look at where the physics takes place in a single layer, which is the Dirac cone at momentum k. So I realized that this was, explained in Alan's talk and in Nicolas' talk and in other talks, and will be probably explained in some more detail today and tomorrow. But I prefer to go through it for completeness. So the physics in single layer of graphene happens at the K point, and then the next layer of graphene is obviously rotated by an angle theta. And in tri-layers, you have three angles. So this is theta 1, and this is theta 2, for example, etc. Or multi-layers, you have more angles. And then from the upper layer, the physics is given by another Dirac cone, which is at momentum, this is K lower, K upper. These two Dirac cones now basically create two separate triangular lattices. Why? Well, the symmetry around the K point is C3, is the symmetry of a triangular lattice, and the two Dirac points create a periodicity which introduces some Moiré vectors and a new Briand zone, which is this small. This is obviously a very large angle description here, but this angle, if this angle is very small, then this Moiré Briand zone is also very small. And this Moiré Briand zone is basically given by three vectors, which we'll call Q1, Q2, and Q3. Okay, and these are similar to the graphene displacement vectors between atoms, but in momentum space. Obviously, the reciprocal Moiré vectors are, you can choose your pick, Q3 minus Q2 and Q1 minus Q2. That's one of them. And you end up having a model, which is this Bicester-McDonald model. So please ask questions if it's unclear, which is basically defined on a series of Moiré Briand zones, first Briand zone, second Briand zone, etc., which correspond to the number of plane waves used in the system, really, etc. Okay, and for simplicity, the momentum, the way we'll use it, is always defined in the first Moiré Briand zone, which is this one, for example. You can pick it to be this one. Then this number of plane waves can go to up to infinity. So, and really it doesn't go up to infinity. It goes to up to when you couple to the next Dirac, to the other valley in the single layer graphing. But since this angle is very small, of order 1 degree, then this is of order 1 over theta. So you have about 100, at least hundreds of plane waves in one direction. So the square of that. Okay, so let's say that the number of Moiré Briand zones things to be taken into account is infinity, first Briand zone, second Briand zone, etc. for beginning. And the Hamiltonian here, which you can understand immediately from real space, but which I'll write in momentum space, is in the first Briand zone, has a term which we call diagonal term, which is a Dirac term, diagonal in plane waves. basically, plus an interaction term, or a hopping term, really. Let's call it hopping between the layers. Okay. And this term, this Dirac Hamiltonian, without this interaction, would be just the folding of the original Dirac Hamiltonian of graphene to the smaller Briand zone of the Moire lattice. And this term represents the interaction between the lower and upper layer. Okay, so let's write them down specifically and find out their physics. So we need to put some indices on the problem. And as was explained before, there's the physics separates, as we explained in basically Alan's talk or Nicolas' talk. The physics separates into two valleys, which correspond to the two K points of the original graphene Briand zone. And you can see that at one valley, so it's called this valley eta equals to plus and eta equals to minus. And you'll see that at one valley, which is eta equals, say, eta equals to plus, I have one Dirac fermion from the lower, this is from the lower graphene layer, and one Dirac fermion from the upper graphene layer. Okay, so I have two Dirac fermions per valley. And of course, spin adds as another multiplicative constant. And the indices for each of these Dirac fermions, I have a sublattice index, which correspond to the A and B sublattices of the original graphene problem, which is called alpha, A and B. And then I'll have a plane wave index, which corresponds to Q, the number of basically points in this new Moire first Briand zone, second Briand zone, etc. Okay, so if I call these, if I make a different coloring with red, I will call the plane waves, for example, for the upper layer. And with blue, the ones for the lower layer. And you can see that, of course, they're staggered, because if this is, well, let me just try it, the wrong color. If this is red and belongs to the K point of the lower layer, then this is blue, this other Dirac K point. So this is blue, which belongs to the K point of the upper layer. Okay, so now let's write down this Hamiltonian. So the Dirac Hamiltonian in the Moire Briand zone corresponds to basically the folding of the original Dirac Hamiltonian. So what you have is, you have a Dirac Hamiltonian, okay, which looks like this, and which is diagonal in plane waves. So this Hamiltonian is, of course, has Q prime, alpha prime, eta valley index, which refers to either we're looking at the physics in this valley, and we want to find out the matrix elements of either the same plane wave or different plane waves. Let's call it alpha and beta, A and B sublattices, or A and A sublattices. So this sigma has indices alpha and beta, and this is just the folding of the original Dirac Hamiltonian. And then you get the interaction between layers, which I think, well, both Alan and Nikolai explained. And this interaction is a parameter, a matrix parameter, Tj, which is Tj alpha beta. And it's a first neighbor basically hopping on this momentum lattice. So delta Q, Q prime plus Qj, sum over J equals 1, 2, and 3, the 3 directions. Okay, so this is the Bicester-McDonald Hamiltonian for the twisted bilayer graphene, and Tj have an expression. There are these 2 parameters. This is sigma 0, which is identity. Cosine of 2 pi over 3j minus 1 sigma x plus sine of 2 pi over 3j minus 1 sigma y. Okay, so this is AA because it's diagonal in alpha and beta. This is AA hopping. This is referred to AB hopping, is off diagonal in alpha and beta. You can see them clear. And this W is in units of V Fermi times Dirac momentums times theta. So this little bugger here, which is Q1, is just, this is the Dirac momentum big K in the single layer graphene, K times theta times the twist angle. Okay, and I can rescale the energy, everything. So this is the interlayer hopping over this K times theta times the velocity of the Dirac fermion. So it's basically a ratio, and this is now a dimensionless Hamiltonian. And just to give you feeling for these ratios, W1 is of the order, 1 over square root of 3 at the first magic angle, or smaller, and W0 is smaller than W1. And these are important, that these things are smaller than 1, and as we'll see later. So just remember that if you go through the motion and obtain the actual values, all of these are smaller than 1 in the regime that we're interested in, which is the small angle flat band regime, the regime where flat bands exist. Okay, so that's the first thing. Now, what can we understand about this model? Yes.
Can I ask a question about the Hamiltonian you just wrote?
Yes.
So basically, it's kind of a very basic question. So this hopping term that you've written, you said that it's a nearest neighbor in momentum space, because usually when we do tight binding, isn't it nearest neighbor in real space? And then, so
yeah.
I'm just a little confused.
It's not a tight binding. That's very
okay.
Good. So this is the K dot P. So in momentum in real space, this would look like.
Oh, I see. It's a K dot P. I see. Okay. Mm-hmm.
This, in momentum space, this looks like e to the IQ times R, where Q are these
right.
Q. So when you expand in plane waves, you're going to get a coupling between the plane wave at Q and the Q prime. So does that completely answer your question?
Yeah, it does. Thank you.
Thank you. That's a very good question. Thanks. Okay, very good. Yes. So yes, there's not a tight binding. So of course, there's tight binding approaches to the twisted bilayer problem, but those have to be almost always numerical, and they involve taking a huge number of atoms per unit cell, which is basically 10,000, because you've got a huge moire unit cell. At the first magic angle, it's around 10,000. So indeed, you have to do this K dot P approach if you want something. If you don't want to be stuck with a huge number of atoms. And this K dot P approach has its advantages, as I'll show now. So the first thing are symmetries of this problem. And the second thing is, do we have to solve this problem or on a computer? So this Q, the number of lattices, this large, do we have to solve this problem on a computer, or can we make analytic approximations to get some feeling of the problem? So the first hint that something analytic is possible is actually was actually given in the original paper by Alan, where they basically solve this model only by looking at what we now call the tripod model. Well, we meaning I, call the tripod model. It's not a generally accepted term, but let's call it the tripod model. So normally you'd have to, you'd have a lot of plane waves to go through and build this Hamiltonian and diagonalize it. But this is what McDonald said. So this is the first Maury-Briand. And they said, well, let's look at just these 4 sites in momentum space. I'm just going to look at these 4 sites in momentum space, call this 0, 1, 2, and 3. Okay, this coupling is T1, this coupling is T2, this coupling is T3. Okay, and the Hamiltonian for these in this basis is just with K measured from this is K Moiré, for example, or K Moiré prime. You can choose your definition. With K measured from here, the Hamiltonian is K dot sigma. This is the Hamiltonian for this site. The basis is 0, 1, 2, 3. K dot sigma, K minus Q1 dot sigma, K minus Q2 dot sigma. This is, and K minus Q3 dot sigma. And here I have T1, T2, T3, T1, T2, T3. And at 0 everywhere. Okay, there's 2 things about this Hamiltonian. Well, first of all, you don't know if it gives a good approximation. I'm just considering really not even a full, not even the Q vectors of the first Briand zone. So I'm just giving a Hamiltonian, hoping something good comes out. And also, it doesn't respect the whole full symmetries of the twisted bilayer because it's an expansion. It's a further expansion around this K point, okay, around this Km point. It respects the symmetries of the Dirac point, but it doesn't respect, for example, it doesn't have C2x symmetry, which the twisted bilayer has because it doesn't contain this point here, okay? But nonetheless, the lesson we learned from this Hamiltonian is that 1, it predicts the magic angle, or it predicts a property that we call the magic angle, that was called the magic angle in the original paper, which is the vanishing of the Dirac velocity at some values of W0 and W1, okay? And it predicted rather well in the sense that if you do a more evolved, if you take more shells, you're going to get basically roughly the same, almost the same value, not exactly the same value, but almost the same value. So obviously this Hamiltonian, if I call this psi0, psi 1, psi 2, and psi 3, this Hamiltonian has K psi 0 plus Ti psi I sum over I equals to E psi 0, and Ti plus K minus Qi psi I is equal to E psi 0. Now notice the reason why I want to point out that this is, well, it's not entirely solvable, but it's solvable with a basic approximation, is that this is K minus Qi dot sigma, is that these 2 by 2 matrices can be immediately analytically inversed. So this psi I here. So this, so for example, psi I, this is Ti psi 0, psi I is equal to E plus K minus Qi dot sigma over E minus K minus Qi squared, Ti psi 0, etc. And then you can plug this in here and find that the equation, the eigenvalue equation for psi 0, after making a small energy approximation, so you assume E, there is a solution for E small, and then find whether there's consistency. And you find out that the eigenvalue equation is Vf times K times sigma psi 0 is equal to E psi 0, where Vf is 1 minus 3 W1 squared over 1 plus 3 W0 squared plus W1 squared. And I remind you that W0 and W1 appear in the expressions of T1, T2, and T3 are the A hopping or AB hopping of the the lower and upper layer. Okay, so notice here that the velocity is reduced with respect to the original velocity. Okay, is reduced by a factor of 1 minus 3 W1 squared. Hence, for W1 is equal to 1 over square root of 3, irrespective of W0 in this model. The velocity, this velocity is exactly 0, and it means that the Moiré-Briand zone, Dirac, so this is the Moiré-Briand zone, MBZ. The Moiré-Briand zone Dirac point has velocity which is now 0. So this was called the magic angle. And this is called the magic angle condition. Okay, so now what I want to point out is that this magic angle condition, as I said, stays the same or almost the same. This value 1 over square root of 3 stays almost the same if I go to larger number of shells. Almost no change in the physics around the K-Moiré point. So the first thing that we want to understand is, why is this? And this gives rise to an approximation in the problem where basically that permeates all through the interacting problem and permeates all through the real space approach of Gang and Vafek and the interacting problem in momentum space approach.
I have a quick question. Before you continue. So am I right in thinking that if you were to keep all the successive Brillouin zones, if you were to keep all of them to infinity around that, would that restore the symmetry that is not kept around that?
Right. So yes, that's a very good point. So there's two ways of restoring the symmetry. First of all, keeping everything, keeping all the as you just mentioned. So one way of restoring the symmetry is keeping all the shells up to infinity. That's a very costly way because you don't want to build an infinite Hamiltonian. But as you alluded to, it's not necessary to do this. The other way is to do a model that's not centered at the Km point and that's centered at the gamma point. And this model, you can build a shell by shell model that keeps the symmetry of the problem. However, it's harder to solve than the Bistrom-McDonald Hamiltonian, but it will give you the physics around the gamma point. So the moral of the story of these models what I'm going to go through at the end, and this is valid for the tri-layer model as well, with one extra simplification, with one extra complication, is that you can focus around several different points in the Briand zone and use a very small number of shells to get the physics around those points. So for example, around the K point, Bistrom-McDonald showed that really close to the K point, it's enough to keep only these four plane waves. We now know that if you want physics around the gamma point and very close to the gamma point, it's enough to keep this 6 plane waves of the hexagon model, of just the closest ones to the, and that has the correct symmetry. It won't give you, just keep these 6 shells, it won't give you the correct physics at the K points, but it'll give you the correct physics at the gamma point. Does that make sense?
It does. Thank you.
Thank you.
May I also ask a question?
Can I ask a question? Sorry.
Please.
So we derive this magic angle condition. I just want to know, how does W1 depends on the angle?
Very good point. That's a fundamental point. So notice that here, let's see. Here, when I wrote these W0 and W1s on this page, I wrote them here with this renormalized to 1, this velocity renormalized to 1, right? Normally, so and this Q here this Q, which this Q was in units of K dot theta, where K was the, right, this Q is the difference between these vectors, small q, the small q vectors are the difference between the lower Dirac node and the lower layer Dirac node and the upper layer Dirac node, and those depend on theta. So these W0, for example, or W1 are just the interlayer tunneling basically over the Dirac velocity, the renormalized, the original Dirac velocity in graphene, Vf times the momentum K. This K is the momentum of the K point of graphene times theta. Does that make sense?
Oh, okay, I see.
So this is how it relates to the angle. Well, this is a small angle approximation. It's Vfk times 2 sine theta over 2. Does that make sense?
Yeah, I see. Thank you.
Thank you. So this is how you relate it to the angle, and this is something that I failed to say. So thank you for the question. Any other questions?
Yes.
Okay.
Is this important that our K-space lattice has 3 nearest neighbors and not more or less or any other configuration?
Right. So
like,
that's
is the honeycomb important?
So normally I would have to solve this problem on a huge number of shells, right? So for example, so this is what Bicester and McDonald took in their paper, right? To find out around the physics around the K point. I could take, the next approximation would be to take this, which is also, by the way, solvable. The next approximation would be to take, so this I'm just going to build up shells keeping the symmetry around the K point, right? So this is if I want to find the physics around K point, and I'm building up shells in a consistent manner, keeping the symmetry around the K point. The next approximation would be to build, to take these ones, okay, and so on. Now, of course, you can also just start from the gamma point, and then this is the first shell, the lowest number of shells if you want to keep the symmetries. So this, if I want to start at the K point and keep the symmetries, I build the shells in a way that keeps the symmetries around the K point. And this way of just building, the next one would be this guy, etc. And so on. So if I want to start around the gamma point, the smallest number of shells that I would build would be 6 plane waves, and then if I want to keep the symmetries, the next number of shells would be this one, etc. So it's just a matter of whether you want to keep the symmetries. If you don't want to keep the symmetries, you can kind of make the lattice weird, but I would suggest keeping the symmetries in the way you build it on a computer, for example. Have I answered your question?
Actually, not exactly. I was trying to ask whether the fact that the model has a C3 symmetry around the K point and not a C4 or C2 or something else is important to get the magic angle.
Well, it has to have a C3 symmetry around the K point because that's the symmetry that originates from the lattice, from the underlying graphene lattice, right? So the K point.
But if I had a different lattice?
Well, if you have a different lattice, then you're going to get a different symmetry, you're right. But for this, so the Bicester-McDonald type approach is valid for many lattices, and then you're going to get a different symmetry that's valid for a different lattice. But for the Moire lattice, it's as I said, it's important to you can't build a square lattice here. It has the correct symmetry. It'll give you the wrong physics. It'll give you a wrong model because it's not twisted bilayer, to be twisted square lattice, etc. Does that make sense now?
Yes, thanks.
Thank you. Very good.
Can I also ask a very basic question? So when we stack 2 graphene layers, what protects the Dirac points? And another related questions in this like tripod model, some symmetries are broken, but some symmetries remain. So what kind of symmetry makes it so that the Dirac point is protected in the tripod model? Thank you.
Very good point. So there's two points to this. So what protects the Dirac node is a symmetry that's C2 times time reversal, C2Z times time reversal that we'll talk about. I don't want to, I aim to talk about it in like 10 minutes.
Okay, thank you.
The next thing then, and I'll get to that, that's very important. The next thing is what symmetries are kept at the K point. Well, this is not really, the K point doesn't break really any symmetries, okay? Just the tripod model, it doesn't break any symmetries. It's just that it doesn't keep all the symmetries of the lattice because it's just around one K point. So for example, it does, this is K moire. It doesn't keep the symmetries around K moire prime, okay? Because I would have another, I don't have that point, but I could build a tripod model around K moire prime also and take the physics of the K moire and K moire prime to be the physics of one tripod model and another tripod model. So the tripod model by itself, this model that was really introduced in the original paper by Mr. McDonald, keeps all the symmetries that need to be kept around the K point. Does that make sense? So it doesn't really break any symmetry. It just doesn't have the other. It's like, it's like looking at single layer graphene only around one K point. Keeps the symmetries that have to be kept around that K point. It doesn't have the other K prime point. This is the same thing here. Does that make sense?
Sure, I understand. Yeah, thank you.
Okay, any more questions? Okay, so large number of shells, what I wanted to point out is that large number of shells doesn't change the physics. And I want to explain this now. So why doesn't it change the physics? Well, or of the physics of the flat bands. So we're looking really at so we know basically this is kind of a posteriori knowledge though. You can build an analytic argument to get it to understand it from the beginning, but we know that this system, okay, at some angles which are very close to what they get from the tripod model, has these bands that look like this, for example. Okay, so this is, I drew them even fatter than they are. This is K, this is gamma, there's some M point here, and there's K prime, all moire, all in the small Briand zone. Okay, so we know that it's got some, and the model has some particle hole symmetry actually also, or close to particle hole symmetry, so very close, and this is close to zero energy. So we know that the model has a set of almost flat bands of energy 0, 2 of them, plus minus 1, say this is, okay, per valley, per spin, per eta equals plus minus, per spin equals up down. Okay, so these guys, we know from numerics, we could find an analytic arguments why they happen. What I want to point out is once we know this, we know that a small number of shells is all we need to obtain a good approximation for the eigenstates of this model. And as I said, this permeates to the interacting problem and in real space to other problems. So okay, so what I want to show you is the argument for this. So let's start, instead of the tripod model, you can build the identical argument around the K point, but I want to build the argument around the gamma point. So okay, so the Hamiltonian, so we're going to build, as I said, we're building this Hamiltonian in shells. So this, call it shell 1. So this is, shell 1 is just these 6 guys. Okay, I call this shell 2. Okay, then you can build the next shell, which is just basically its graph distance. The next shell is just these 2 guys, okay, etc. Okay, I'm not going to, or maybe I do, etc. This is shell 3, okay, and the Hamiltonian really is K minus Q times sigma plus sum over I T I delta Q Q prime plus Q I, where Q1, Q2, Q3 are these guys. Okay, these vectors. So this is Hamiltonian. So now notice that this Hamiltonian has this high ramp up term. This K belongs to the first Briand zone. So this K belongs just to this Briand zone. And this is a ramp up term where this Q is the Q of the shells. Okay, so for example, so I'd pick my origin here. This Q is measured from the origin. Okay, so large shells have large Q. So shells far away from the origin have large Q. Okay, so normally you have a Hamiltonian that has a term which in an infinite number of shells goes to infinity. This term, if I for Q large away from the first Moivre-Briand zone, this term will go to infinity. So you have a Hamiltonian with a large term which goes to infinity. You would think that large shells are very important, but actually it turns out they're not. They're exponentially unimportant for the physics of these bands. They would be important for the physics at the bandwidth, but this model has no bandwidth because it's a continued model. So for these bands, this is not important, and this you can see immediately from a symmetry argument. From a quantitative argument, not from a symmetry argument, excuse me. So from a quantitative argument, you can see it immediately. Why? Well, if I focus on the physics of the Q's shell, okay, then this physics will have some coupling to, the Q in the nth shell will have some coupling to n-1 shell. You'll have some coupling to the n+1 shell. So for example, this shell 2 here will have some coupling to shell 1, will have some coupling to shell 3, etc. Right? Okay, so let's neglect the coupling to the n+1 shell. Let's say I'm building the Hamiltonian on 100,000 shells, and I want to just look at the outer shell and then find the physics of the 100,000 minus 1 shell, etc. And let's see what the structure of the Hamiltonian will look like. Well, this is a diagonal term. So I have this K minus Q sigma times the wave function of the nth shell. Okay, and the nth shell couples by Ti, by these T's, this is T2, this is T1, etc. You can fill in your lattice there, couples by T's to the n-1 shell. Okay, this is kind of written in Cavalier notation, but you can actually, it's not that Cavalier. This is actually the structure if I build a matrix. So this is some T matrix that depends on how far I've gone to the shell, its actual entries, but nobody can deny that this is a matrix formed out of these T1, T2, and T3. Okay, and this is the n+1 shell, n-1 shell, sorry, this n shell. Okay, and the eigenvalue equation says that this is E times psi of the nth shell. Okay, that's the eigenvalue equation. So now you can back out psi of the nth shell. This is 1 over E minus K, 1 over E minus K minus Q times sigma T psi n-1. And this is a fundamental quantitative equation that immediately gives you the perturbative expansion of this model and the understanding of why upper shells don't matter. Why? Well, K belongs to the first Briand zone. So absolute value of K is less than 1 in these units, 1 meaning in units of, K theta, which is the graphing vector times theta. So K is 1, this distance is 1, okay? So, or this distance is 1. Okay, so K belongs to the first Briand zone is less than 1. Q, okay, Q is the shell the outer shell. So Q for large number of shells is much larger than 1. Okay. And this T, since it includes T1, T2, T3, as I said, is of order 1 over square root of 3. It's got terms of 1 over square root of 3 in it. So and we want to focus on low energy states. So E is close to 0. And this 0, meaning this is actually, this is much smaller than 1 by 2 orders of magnitude, actually. So 0 is a pretty good approximation. So what we find out if we neglect this, if you put this to 0, and if you put this, I'm going to neglect K with respect to Q. I'm going to also neglect K with respect to Q. And this is the Q of the nth shell. What we find is that psi of the nth shell is of order 1 over Q of the nth shell, okay, times T times psi of the n-1 shell, okay? This Q of the n shell is of order n, okay? And this is of order 1 over square root of 3. And you immediately have that psi n is much, much less than psi n-1 for n large. Okay. So in other words, your amplitude, the amplitude, so I have these flat bands. These are the passive bands. And I have these flat bands. Then I'm trying to find the amplitude of these flat bands on, the wave function Q, on the sites of the plane wave Q, amplitude alpha, valley eta, and momentum K in the first Moire-Briand zone. And what I claim is that for Q goes large, if I want to find out, right, so I have these shells and I'm going to diagonalize my Hamiltonian, I'm going to get an amplitude on each of these points. If I want to find out the large, the wave function on the outer shells, this will be very small. By the way, this is an exponential decay because of course psi n-1 has the same 1 over n-1 t psi n-2, etc. So you can immediately see that your wave function decays exponentially. The amplitude of wave function on outer shells decays exponentially with respect to the wave function on the inner shells. Okay.
So Andre, just so you know, we're at about the 45-minute mark.
Okay. Okay. Very good. I'll just 2 minutes, 3 minutes.
Sure.
Please. Okay, so you can see that the wave function decays exponentially as I go to outer shells. And moreover, what this, you can ask, how far exponentially. So basically this immediately tells you that outer shells are not important. And this is the comment that Nicolas made, that by computer, once you go to 6 shells, you reach machine precision. So you reach 10 to the minus 14th of all the weight of the wave function is contained within 5 or 6 shells. Okay, because this is smaller than 1. This is, of course, gives you the exponential decays for outer shells. And you can ask how good, if I don't want to reach machine precision, if I want to see it by eye, how good, how many shells do I have to go to? And it actually turns out that once you've reached the 3rd shell by eye, you don't see a difference. So for example, if I wanted to solve the Bistritzer-McDonald Hamiltonian, and this is the fact of, this is the reason for this is that this t is also smaller than 1. So in this n, this n is 1 over 2 times 1 over square root of 3, and you take this to power 3 shells, then you're going to basically not see a difference by eye. So if I want to obtain the physics, if I want to get the bands of the twisted bilayer graphing, even this model here gives you a pretty good approximation in the sense that, it's within 10% of the actual flat bands. If I add the next shell, which is this guy, okay, etc., then I will see no difference by eye with the actual band dispersion of this model. Okay, so the moral of the story is that these wave functions far away from here do not matter anymore. And this has a fundamental property on the many-body state, which comes through the form factors. So as Nicolas and other people explained, basically what we're going to have to build, and this is, I'm going to show this next time, what we're going to have to build for the many-body problem are the overlap matrices at momentum K and Q plus G, where G are the Moiré-Briand zone vectors. This is the Q, these points are the Q lattice, the big Q lattice, okay? And this is value dependent, has two indices, which are band indices. This M and N either tell you whether you're in the M equals 1 or M equals -1 band, okay, in the two bands of the two flat bands. And as always, when you project, this is a general statement, you project an interaction or anything you want to do with a Hamiltonian, you're going to have to build these overlap Berry phases. You're going to have to build these overlap wave functions. So this is U of K. This is the eigenstate of this. Call it U of K of on lattice site Q. Of band M, sublattice alpha, spin S, valley eta for all the indices. This is diagonal in spin, so they don't depend on spin. So we can just neglect the spin. Overlap K minus Q, Q minus G, N alpha eta. Okay, so you can see that this is basically the overlap of the state at K, of the M state at K in valley eta, with the overlap at state K minus Q and Q minus G. If I was to do it per plane wave, and eta. Okay, so just look at it in this form. Okay, so now what I want to point out is two things. You can, first of all, you can clearly see that this looks very similar to a Berry phase. In fact, it has to do with, well, Berry phase and Fubini stoichiometric, but that I won't have time to go through. But I want to point out that when G is equal to 0, how do I, when G is equal to 0, this is exactly the overlap of two states, right? So when G is equal to 0 and Q is equal to 0, okay? When G is equal to 0 and Q equals to 0, this M is delta Mn, because it's the overlap of the eigenstate at K with the eigenstate at K, the eigenstate M at K with the eigenstate N at K. So, okay, so this doesn't depend on K when Q is 0 and G equals 0. For G large, and, you know, large meaning larger than square root of 3, which is larger than the first vector. So this G equals square root of 3 is one reciprocal lattice vector. For G larger than square root of 3, what you're going to have to take is the overlap of a state at some Q here with an amplitude at some Q here, with the amplitude at, say, Q minus G, okay, which would be here. Okay, so I'm taking the amplitude of the state on these two sites, for example. But I've argued already that as you move away from the center, okay, these plane waves, these eigenstates, the amplitude vanishes dramatically. Okay, so for G larger than square root of 3, so for G for vectors larger than square root of 3, this M K Q plus G is negligible. So you can take it to be exactly 0, and you can quantify how negligible it is, but it is negligible. So the only M that matters and this is for any Q, by the way. So the only M that matter are M, K, Q. So this is the G equals 0, and M, K, Q plus G, where G is square root of 3, or the amplitude of G is square root of 3. So this is just the first wave vectors. Okay, so the moral of the story is that there is an approximation to these Bistutzer-McDonald Hamiltonians are an approximation. You can make an analytic approximation. They are built on shells. The amplitude of the wave function decays as I go to larger shells, and this has important consequences for the form factor. And one of the consequences for the form factor is the fact that in the form factor, in this amplitude, this overlap, which is, we'll call it the form factor, this M matrix, you don't have to take into account larger G's than the first reciprocal Moiré-Briand zone. And this simplifies your interaction considerably and allows you to get some approximate states, allows you to get some exact states too, but it allows you to get some approximate many-body states. Okay, so I'll just stop here. And also this is true also for the tri-layer. This doesn't have, and I'll show you this next time.
Great, thanks, Andre. We have time for a couple questions. Let's start with Adamya.
Hi, thank you for the talk. I just wanted to ask in this last screen that you just had before. So the form factors being only the near shell form factors being the only one that are relevant for the interaction. Does that kind of imply
Hello?
that the interaction
I couldn't
in
hear
real
you.
space is? Hi, hello. Am I audible?
Sorry, yeah, I couldn't hear you. I think it was my internet. Could you repeat the question, please?
Yeah, so I'm just asking that does the fact that, so these form factors are for the interaction, right? If I'm understanding this correctly.
They are what?
For the interaction, right? You projected the interaction and these are the
Yes,
form factors.
these are the form factors.
So my question is that,
yes.
So my question is, since these are only like most of the contribution only comes from the inner shells or the nearer shells, does this kind of imply that it's a long range interaction in the sense of at graphene scales in real space? Can this be? Yeah.
Yeah, so that's actually a very good question. The long rangeness of the interaction is the way or the short rangeness is the way this varies with Q. So this actually is not a long range. So this is part of the approach, the real space approach, and you can read Oscar and John's paper, and their Hamiltonian, which is made in real space, basically involves only close, very close, like on the Moiré scale, it involves nearest neighbors in the
okay.
Yeah, that's a very good question. So in the real space approach is basically it's going to have some it will have some exponential tails, but it's not long range. It has it has some operators on the interaction itself. When I'll get to it tomorrow, but basically the interaction itself has on plaquette operators, basically.
Okay. Okay. Sorry, I have one small question about this index alpha. So this alpha you mentioned is a sublattice index, A or B. So I'm slightly confused. Sorry?
Of the original, so it's the same sublattice index as the original graphene. Right? The original graphene
right.
also has A and B. Yeah.
Oh, okay. I see. I understand. I understand what you
When
mean.
you write this k dot sigma in the original, right? So when I write down the k dot sigma Hamiltonian in the single layer
Yeah,
graph,
yeah. It's written in the AB sublattice spaces, right? Yeah. Okay, got it. Okay,
That's
thank you. Yeah.
very good. Thank you.
Okay, we have another question from Dimitri.
Hi, thank you for the talk. So I have the following question. So suppose, in this approach, we require that we have a mini Brillouin zone, which means that we have a commensurate twist that we can basically connect Moiré unit cell somehow, and then we can fill the original Brillouin zone with these mini Moiré Brillouin zones. Then the question is this. So this is quite a strict requirement, which means that we have to fit exactly among all these twist angles to the ones which give us commensuration, which basically requires to a certain extent that we have to implicitly think that there is a lattice relaxation that we always get this solution. But then the question is, okay, if we have a lattice relaxation, how we should justify the chiral limit, which basically decouples to a certain extent the two layers?
Right. So this is a very good question. So first thing that I want to point out is that commensuration is, ideally, it's not really a problem. You don't have just a set of angles, right? So I can always get commensuration is two integers, right? And I can always fit very close to any, right? If I give you a 1 over square root of 3, I can fit it to whatever precision I want to by a ratio of two integers, right? So I can get commensuration if I want to, exact commensuration, right? So that's the first comment, but that comment should also basically point out that exact commensuration is not really fully necessary, right? So basically, if the same number, irrational number, say some angle that you want, can be expressed as a ratio of two integers to as good a precision as you want to, and these, or there's different ratios of two integers, and basically this tells you that commensuration is not really important. And this is actually what's happening here. None of this is actually exactly commensurate, right? So indeed, if I wanted to get, as you're right, that if I wanted to get a model, if I wanted to get, so notice that I haven't spoken about the other valley very much. Well, mostly because one, I can just transform one Hamiltonian to the other valley. But two, if I would take this, I wrote it down poorly here. Anyways, bear with me. It's a poorly written Brillouin zone, should be rotated. But if I wanted exact commensuration, what would happen is I could build a Moiré Brillouin zone here. I could build a Moiré Brillouin zone here, and then they would fit exactly. If I would tile up this large graphene Brillouin zone with these small Moiré Brillouin zones, it would tile up exactly so that it fits this one. I didn't make this requirement in what this is kind of a feature of the Bistro-McDonald models. In what I've spoken, I haven't made this requirement. So basically, for non-commensurate angles, the only thing that you're giving up is the fact that if you tile this lattice, you're not going to hit exactly the K prime point of the original lattice. Okay, so it's certainly close to some commensurate angle, because anything is close to some commensurate angle, because the commensurate angles are some ratios of integers. You can find them exactly. So any angle would be close to some commensurate angle. And if I tile up my Moiré Brillouin zone that I've spoken about and try to hit the K prime point, if I tile up the Moiré Brillouin zone on K and try to hit the K prime point, I won't hit it exactly if I'm not exactly commensurate. But that doesn't prevent me from writing down this model in momentum space, in Moiré Brillouin zone momentum space, because the block periodicity, which is just the only thing that's necessary to have this model, the block periodicity of the Moiré Brillouin zone is due to the fact that I have an infinite number of shells. So for example, remember I was talking about this infinite number of shells, etc., blah, blah, blah. And I had the operator CK or CKQ, where Q belongs to these shells. CKQ and alpha, eta, blah, blah, blah. So now if I want CK of K plus a reciprocal lattice vector, Moiré reciprocal lattice vector, the block periodicity will basically tell me that this is the same as the CK Q minus G alpha eta. But if my Q goes to infinity, I will have block periodicity because I have all the shells, right? So if Q belongs to the shells, Q minus G will also belong to the shells. So the block periodicity is not, and this is the fundamental thing, the block periodicity of these Bister-McDonald models is not due to exact commensurability. It's due to the fact that I build the K dot P with an infinite lattice, for the states around the zero energy or for the low energy states, you have a pretty good block periodicity. If I went to high energy states and tried to connect the two K and K prime points of graphene, I wouldn't have it. Does that make sense?
Yeah, sure. Yeah, but I was thinking more of certainly that is a part of the question. But the other part was, at the end of the day, we know that there is lattice relaxation, which plays a role, right? Which necessarily couples things. But then the Chiral limit, we sort of remove this coupling. And how justified is that?
Well, so you can justify, so there's several ways. Well, nobody said that the Chiral limit is an exact description of the TBG. In fact, it's not. Right. So certainly, the bandwidth are not. Well, how should I phrase this? There's many layers to your question. Is the Chiral limit a good approximation of the TBG? I'm not. Maybe the fact that I said certainly not is not entirely correct. The band structure, the minute details of the band structure are certainly there and could be important, but I don't know if the Chiral limit is an exact, well, certainly it's not an exact description of the TBG problem. Now, what you can say is that so Oscar has this RG approach where it basically looks at how these W0 and W1 flow as you integrate out shells from the UV. And he sees that W0 does go down. Now it doesn't go down all the way to the Chiral limit to 0, but it does go down. Now, the other thing that I want to point out is that the flatness of the bands doesn't really change much between the Chiral limit and W0 equals 0.8 W1, which is the what's expected of twisted bilayer. So, and of course, the many body phase diagram has some changes. It's not you get in the Chiral limit, you get some insulating states. In the non-Chiral limit, you can get some metallic states. There's some phase transitions along the way at some fillings. So it's a complicated. The Chiral limit is good because you can solve some things exactly. You can solve some things exactly in the non-Chiral limit also. It's just a simplification of the model. How good, how faithful it is to the physics of TBG, that remains to be seen. There's some faithfulness, there's some unfaithfulness. Does that make sense?
Yeah, thank you very much.
Okay, we have time for one last question from Aravind.
Hi, I have quite a very basic and silly question. It's about the shells. So the fact that the wave function gets an amplitude that goes as 1/n as you go to every outer shell, does that already take into account somehow the fact that there are more number of points that go as you go to outer shells? So if the number of points that go as n and the wave function goes as 1/n, you might still have a finite contribution, right?
Right. Well, yeah. So that's a very good point. Actually, it's so first of all, each wave function of the scales as 1/n. So if I was to look at the wave function of some shell far away, it's exponentially small with respect to the center, right? Whereas the diameter is
goes polynomial, some square or something.
Polynomial, yeah, or linear, yeah, perimeter basically, right? So certainly it's not enough to compensate. So you can now, it might be enough in some percolation problems because you have a lot of the percolation problems. You might have a lot of path, right? But that I don't know. But certainly in when you're computing form factors, it's not enough to compensate because if in these form factors, if I sum over G, so if I have this M K Q plus G, which is really U of K plus Q G plus, I wrote it a bit different in the previous case. I wrote it as K minus Q, Q minus G, but it's the same thing. In this case, if I, for say I sum over G, I'm going to sum over at some shell, I'm going to sum over a polynomial number of G's, but these will be, if G is large, this will be exponentially small. Does that fully answer your question?
Yes, yeah, perfectly. That's what I was looking for. Yeah, thanks.
Thank you. Yeah.